start 1 minute early. Our next speaker is Lekili, and he will tell us about fable of Fargues-Fontaine curves.
Okay, thank you very much for the invitation. So first I'd like to say I'm great admirer of Kanji Fukai's work and his personality also. So his theorems as well as theorems have been very important in symplectic geometry. So, thank you and happy birthday. So today I'm going to talk about. So this is some kind of mirror symmetry story about Fargues-Fontaine curve, and the mirror is going to be two torus, but with some modification, so which I'm going to explain. And this is joint work with David Truman, and it's really in the spirit of this conference. It's a report on what we are doing. So I won't really state the theorem. I'm just going to tell you some key new ideas and a calculation, a new calculation. Okay. So I made a plan of what I'm going to do. So the first part will be, so I don't expect people to know what this Fargues-Fontaine curve is. So maybe, even though some of you may, it's kind of a object of periodic Hodge theory. So that's so I'll give a poor man's introduction to this. So, and then, so afterwards I'll talk about what we can do. So that this modification in Fukai categories, and then a new computation. So that kind of justifies why I say that this is mirror to this. Okay, so let me start. So let X be a smooth projective variety, and let's begin with over a field of characteristic 0. Okay, and then so we have two kind of vague homology theories associated with this.
Switch bands.
Yes, switch bands.
Okay. So these are H Durham and H et al. So this is this is a K vector space, and this is a let's say. So we take a algebraic closure of it, and we take QP coefficients. So this is a QP module, which has a Galois action in it. Okay. And so any good student of geometry should know. We have an isomorphism between H Durham and H Beatty. So this is singular homology, and this is given by integrating algebraic forms.
What is it also like by C?
Sorry?
C.
Yeah, let's say KC. Yeah, I switched to KC. Sorry. integrating algebraic forms over topological cycles. So it's the period. Okay. And
Betty.
yeah, singular cohomology. Okay. So, and there is another isomorphism that relates this Betty to étale cohomology, and this is Artin comparison theorem. Okay.
Some issues with your coefficients.
What do I have? Yeah, so this is yeah. Okay. And so if you have any, so I should not write here, or yeah, let's finish this point. So if you have, so this kind of shows you that if you have any ring B where QP and C kind of embeds, then we can relate the étale cohomology. And there are. Okay. And so there are many experts in this room that studies this. This is just the beginning of the story. Okay, so now, so what I want to go to is when I change this field to a characteristic P. So now what happens? So let's assume K is a local field. So like let's say QP or some extension of it. Then we want to relate H to round. And so we don't have singular cohomology, but we still have this étale cohomology. So and H étale. Okay. And so first, in order to somehow do anything, any relation with this, we have to pass to, we have to make QP look closer to some kind of place where we can do analysis. So there, this is easy. So there's QP. So remember, QP is just this completion of Q where P squared is sequence exponentially converges to 0. Right? So that's, but it's not algebraically closed. So for example, square root of P is not here. So you can take its algebraic closure, but then you lose that it's complete. So you have to complete it as well. So and that's called CP. Later completion. And then you can ask if I tensor this with CP, say are they isomorphic? Right, so that's a place. CP is a place where we can integrate things and do the usual analysis. So, but so there's something wrong with it. It's not enough. So what happens is CP does not have. So after going to this completion, it does not have pi. So even if we take x to be GM, for example.
It's 2 pi I.
Yeah, it has I, but it doesn't.
2 i's.
2 i's there. It does not have pi. Yeah. So even for GM, it's not. You can't write a map between these things. So But basically, that's the only problem. So once you add pi in some kind of formal manner, then there is an isomorphism. So this is a so let me just write it. There is a ring B de Rham. And then we have isomorphism like this. This board is too small. Okay, and this B de Rham is somehow non-canonically isomorphic to CP adjoint a variable. But so if you so this is a really bad way of describing it in a sense. It's so there's a somehow there's a filtration on this. So this is what's called a Hodge-Tate one. This theorem is very famous. So it was, I guess, it was first proved by Faltings, but then there are many proofs. So one particularly interesting modern proof is due to valence. So, all right. So now. This B de Rham is basically what's called a period ring, and there are many other ones. So if you try to learn about these things, you get confused because there are many period rings that relate to different cohomology theories, and sometimes they don't relate to anything. So there is a B de Rham is period rings. So I think most of this theory was initiated by Fontaine. But so there is a I don't know, there is a B crystal, and there is a so somehow this is a slightly better one than B de Rham because this additionally has a nice Frobenius action, and the kind of another interesting one is so this is a Frobenius action. The fixed points of the Frobenius action. These are subrings of this B de Rham. Okay. And there's similar comparison theorems that involves these paths. Okay. But so.
What's the bottom thing you wrote? So crystal, are they both B crystals?
One
of them is fixed points.
It's the fixed points of the Frobenius.
Upper fables of this.
Okay. And somehow this is the most exciting one, I guess. So that will relate to this Fargues-Fontaine curve. This is a principal ideal domain. So that's a kind of a big theorem of Fargues-Fontaine. And so let's now try to get closer to what I'd like to say. So there is a curve x. So this is a curve in some sense, and it will have so x. It is a distinguished point. So x minus infinity will be this spec of this ring. And the completion of the local ring at infinity will be this ring of integers in either arm. So this is again a complete valuation ring, non-discrete. So there's a curve that so I'll list. So next I would like to list some properties of this curve, but somehow the main interest in this curve is it kind of compiles together a lot of previous results in periodic Hodge theory into something that's much more understandable in a sense. So let's see. So let me.
Wait, so the completion infinity is what? Is B the wrong?
Yeah. So this is a complete valued ring with
yeah, that's I'm trying to figure out what that symbol is.
plus.
Plus, it means like some kind of.
It's the ring of integers.
Okay.
Okay. So right. So somehow this. So let me describe this curve. Okay. So let's begin with first describing its properties, and then I'll give you a construction of it as well. So it's actually associated to several choices. So E is a discrete relation ring. So this could be characteristic P or characteristic 0, and so the ones that I have in mind are Fp with a variable attached. Discrete relation field. Field of fractions of a discrete relation. So, local field. Yeah. So what should I write? Local field. Okay, and it's going to be either Fpx or Qp. So E. And or finite extensions. And F is a complete non-discretely valued field of characteristic P. So this is also known as a perfectoid field of characteristic P. So it's and this could be somehow we can take Fp with we add all the we add all the pth roots of T, and then we take out algebraic closure and completion. So this is one example. Another example is what's called Hahn series. So this Hahn series is a series of this form, a n t to the n. But n is an element in Q, so rational numbers, and the set of an such that the set of n such that an is not equal to 0 is well ordered. So that's a concrete example.
Why is it characteristic?
Sorry?
Why is it characteristic P?
Why is it characteristic P? So because I wrote it wrong, right? So yeah.
AN are
in F.
Okay.
Yeah. N is in Q, but AN are in F. Okay, so right, and there are many other ones that one can consider. For example, one can also consider Novikov field. Okay, so and this curve is associated with these two. So for each E and F, we have this curve. And in fact, there is another choice involved in its definition, which is a so-called pseudo-uniformizer. So this is simply an element of F. So this is a pi. Which is somehow the norm. The norm of this is less than 1 and greater than 0. Okay. It's a topological nilpotent unit. So the curve does not, in the end, does not depend on this, but the choice of this gives us this the point infinity. So that's where it's going to come in. Okay, so let me list some properties of this to convince you that this is a nice thing. Even though, so first it's regular. It's Notarian.
How did E appear?
There's no connection between E and F, they're just independent of each other.
They are just independent of each other.
But where did E? I mean, you
I'll tell you. I haven't yet
okay.
constructed. Yeah.
But I thought it was independent of.
The curve is independent of the pseudo-uniformizer. But E and F, it depends on E and F.
Ah, okay.
Yeah. E and F are but basically there's these two different flavors that are of interest. So one of them is mixed characteristic and the other one is equal characteristic. Okay, so, and the curve is linear over E. Okay? So this is however, the main point is that if you work with these rings, you immediately know that it's not going to be finite dimensional over E. So it's not finite type over E. So it's regular Notarian one-dimensional. And then it's complete in some sense. So there is a good divisor theory. There is you can do line bundles and so on. It has, so in some sense. So it has an arithmetic genus 0. So H1 of O of this curve is 0. Okay. There is a construction. There are two different flavors of this. There is an analytic construction and there is an algebraic construction. But there is a Gaga theorem that's because of this completeness. The study of vector bundles and so on are equivalent in both ways. So I won't really detail that. So, but there is a graded ring. S0, S1, and so on. So S0 is isomorphic to this E, and the curve X is Proj of this S. Okay. So it has very, very nice properties, and
It's not a curve over E or over spec E?
so it's linear. Yeah, it's linear over E, but it's not finite type over E. Okay, so that's a kind of a.
Well, it's like taking algebraic variety and throw away everything of dimension 2.
Sorry, what did you say?
Take algebraic variety and throw high dimension. Throw away everything of dimension 2 and bigger.
Okay.
That's roughly.
All right. So, but so somehow the interest of people in periodic Hodge theory, as far as I can understand, is this plays the role of twistor line in periodic Hodge theory. So this is an analog of twistor line in usual Hodge theory. Okay, so somehow the point is so we have these different cohomology theories. They give you, so in the complement of infinity or near infinity, they give you two different trivial bundles, and they are glued by this comparison theorem. Okay, so you get a vector bundle over this curve. Okay, so so let me just write. One can express the round comparison theorem that I stated. Yeah, and other parts of periodic Hodge theory in terms of vector bundles on X. And finally, let me say, there is a classification of vector bundles on X. So there is a very nice classification. And it's,
Actually, you didn't say what are E and F in a standard example going to be derived.
Right. E is going to be, I guess, QP in this standard example. And, well, F, I mean, F you can take, well, CP and adjoint T. So you can take CP and...
Should be reduced to P.
Right, so wait. So you could take that and then you could tilt it. So there's this operation called tilting. But since so somehow I'm about to be done with this review, and because I won't be able to do anything in mixed characteristic today. But so let me finally say there is a nice classification of vector bundles. So any vector bundle is a direct sum of stable vector bundles. And any stable vector bundle is isomorphic to O of lambda for some rational number lambda. So this is rank, so somehow slope and rank. So once you fix the slope and rank, there is a unique stable vector bundle, and any other ones are direct sums of this. Okay, so this is very much parallel to, I don't know, P1 or twistor line. So there's this classification. Okay. So so for those who are interested, here's an explicit construction of this here. So how much time do I have? There's no clock.
5 minutes.
Okay. Right. So there's a string called A-inf, and this has two. There's depending on whether you're in mixed characteristic or equal characteristic. There's two forms of it. So one of them is you take bit vectors of OF. So F was this field. You take a ring of integers and then you take your field, so FP with vectors of FP, so this is FP, and you multiply with OE. So this is in mixed characteristics. And the other one is OF, so tensor FP OE. So this is an equal characteristic. And now, so again, in the standard example, you take P is equal to QP, you just get this one. And then here, if E is FP with T variable attached, you just get OF with T variable attached. So, and now we consider YEF. So this is a definition. So this is a adic spectrum of A-inf minus well, this pi that we chose times so let me specialize here. So E is sorry. So again, there's two versions. So either in mixed characteristic or equal characteristic. So this is the one in mixed characteristic. So you have the Teichmuller representative of this pseudo uniformizer. So that's here, and P is here. So you remove the locus where these two are 0.
So say again with the W, what does it say, W bar?
So this
Oh,
is a
that's
pi.
uniformizer. Ah,
This
okay.
is a uniformizer, and then you take a Teichmüller representative of it in the width vectors.
Okay.
Okay. But today we are not going to do this mixed characteristic one. We're going to do the equal characteristic one, and that one is so there's mixed. So that one is defined similarly, but you take so somehow you replace. You don't have to do this Teichmüller representative, and instead of P you have a T, or we call it Z, I guess. Okay, so E is F P Z. Okay, so I'm not going to use this description, so I don't want to spend more time on what SPI is. So this is some adic spectrum. There are many ways of thinking about it. So I learned about one definition of it from one of the lecture notes of Peter Schulze. So it's called SPI in the sense of Huber, but.
Can you say again what's written after spa and spa and?
The pi times z is equal to 0. So this is where the locus z equals to 0, and where the locus you just invert z and pi. Okay, so this is if you take E is equal to this one, this will be just OF with z, and then you invert z and you invert OF. Sorry, you invert pseudo-uniformize. So, okay, so there is an action of the Frobenius on these two parts. Okay, and that action acts on this space, and XEF is by definition. So the adic version is YEF modulo this sigma, action of sigma. This is the Frobenius action, and somehow you have to check that this action acts properly, discretely. So there's a kind of a map from this space, and the action moves to 0 infinity, and the action moves very map. So that proves that this quotient is well defined, and you can take this quotient. So that's the construction, that's the adic construction. Okay. But the one that I'm going to use explicitly is not this one, but it's kind of related. It's this Proge construction. And now let me restrict the equal characteristic from now on. So we have this ring B, and this ring is very simple in equal characteristic. So you take series in so somehow infinite series in both sides, and so AN is in F, and AN times rho and goes to 0 for all rho in 0, 1, and as n goes to infinity, so it is in both directions. Okay? So this is the ring of functions in Y. Okay? And this is this kind of ring you may have seen before. It's for example, it appears in a paper of concept. So there's kind of torus vibrations. So very analogous structure.
Or toolbar, yeah.
Yeah. So and it also appears in this setting. So and somehow it's some sort of completion to allow both sides. It's a series that goes in both sides. So it's much harder to describe the corresponding B in the mixed characteristic. So it involves this several norms and then a kind of pressure transmission. So it's maybe is in your talk. I'm not sure. So I'll stick to this one. And there is a Frobenius action on this. And it's kind of this, what you imagine. So an z to the zn sum goes to an zn. Okay? And we divide by this action. And we take the proj of that. So let me write. So XEF is so the proj of the ring greater than or equal to 0 of sigma is equal to z to the n. So it's very simple. So now it's I guess there's this world that was a bit far away from us, but now there's this ring, and then there's this sigma, and then we have these homogeneous pieces, and then we take its proj. So this is what Fargues-Fontaine curve is in equal characteristic. So, right, so what I want to do next is I want to construct this ring, calculate this ring within the Fukaya category of the torus. Okay, so that's what we can do. But let me review a little bit of the Fukaya category of the torus. Okay, so first let's consider T2 with its fast symplectic form, and so what I want to first discuss is how you prove. I mean, this is just a review of how you prove the standard kind of mirror symmetry statement when you have a Fukaya category of the torus. It's isomorphic to the derived category of the Tate curve. So there T is this, so maybe I shouldn't get Tate curve. Okay. So somehow so there is a paper that I was part of like 10 years ago. It was joint work with Team Perutz. So we proved this kind of result, and it was so rather than the result, the proof is kind of relevant. So I want to review very quickly what the proof involves. So we have so first of all this will be over Z adjoint Q, and so Q is the Novikov parameter. So we have this. We just take these two curves. And they generate the category, and we consider an algebra A, so L naught and L infinity. We consider the endomorphism algebra, but the cohomological category algebra. So let me just say and of L0 plus L infinity. Okay. So this is a very simple algebra. So it looks like this. And any triple composition is 0. Okay, so if you go through 3 times, it's 0. So what we considered is the moduli of A infinity structures on this. And this was a kind of a similar thing. It appeared in the Efimov style, but so somehow this was, I guess this was the first time this idea was used. So this moduli turned out to be equivalent to the the well-known somehow, so moduli of, they will qualify this as minimal A infinity structures that are not formal. So, and up to gauge equivalence and up to C star action. So this was identified with P46, so this moduli of elliptic curves. And so the point is, if you have an elliptic curve, if you take the structure sheaf and a point skyscraper sheaf, the endomorphism algebra of that gives you an A infinity structure on this algebra. And all A infinity structures on this algebra are realized that way. Okay? So first, so you understand that. So then you say that category of torus is going to be one of these curves. Okay? Because of that result.
You need to know M6 and M8 to...
Right. So but it's going to be one of them, but which one, right? So M6 and there's a Hochschild homology computation. So since you know, you refer to that. So the kind of J invariant of the elliptic curve can be computed from the obstruction classes of the same infinity structure. So by the way, let me just advertise this kind of an idea. I worked on several papers on this. So that originally it was in our paper with Tim Barrett's, but then there is extension. So I wrote a paper with Polishchuk, and Polishchuk. So this was about M1N, and Polishchuk wrote another paper, or maybe several other papers, about hierarchies, so that's and some other data, so that was used in Diffie-Morse talk. And recently, I also wrote a paper with Kazushi Ueda, where we relate to moduli of K3 surfaces. So this idea somehow has been useful in proving mirror symmetry in many cases. But so first you identify your Fukaya category as in a moduli space of some given by some algebraic varieties, and then you have to decide which one it is in this moduli space, and for that you compute the homogeneous coordinate ring. Okay, so this is computed like this. So you consider HF. So in this particular example, you consider HF L0 with the interval of L0 around L infinity n times n greater than. Okay, so this ring is somehow a priori we know that this is isomorphic to hom ON for some curve, right? And from here we compute this equation. So that's the idea used. So next, I'll introduce this modification of the category of the torus. So we have this thing called the F field. So the rest of the talk is as follows. So I'll introduce some kind of modified Fukaya category. And in that modified Fukaya category, I'll consider this ring, and this ring will turn out to be equal to the ring that I discussed for the Fargues-Fontaine curve. So what's this modification? So what we do is, so now I'm in symplectic geometry, so I don't need notes anymore. So at each point x of the torus, we consider a field. So lambda x field. So this field varies in our space, and if gamma is a path from x to y, we have a isomorphism from lambda x to lambda y. Okay. So the point is this is a locally constant field. So I understand Maxime talked about this last year. Is that what you said? But so So I learned about this from the paper of my collaborator. So he has a paper in 2017. So where he considers this fields varying on S3 minus a knot. Okay, so he considers a kind of a locally constant field with so whose slope is FP, and so here's a very nice result that says that if you consider this a knot in the complement, so let me just say this result. So I
Yeah, we have no idea what you're talking about. You collaborate?
David Trump.
Okay.
I'm going to write it, yeah.
From
Yeah. So you consider, so this is aside, this is just this definition is to make it clear what it's kind of meaning. So you take a S3 and you take a knot, and you consider a degree n map to S1, okay? So this S1, what? What?
H1.
It uses N on H1.
Yeah.
Degree 1 is not.
So this S1 has a, you take an FP, and, sorry?
F bar.
Why?
Because you want.
Yes, of course. Yeah, sorry, you take some FP bar, and then you take a Frobenius action on this FP bar, okay? And then you pull it back to here. So you get a locally constant varying field. And then you use, his theorem is, so the number of isomorphism classes of invertible modules. So let's call that K bar, and then you consider this F star K bar. So invertible F star K bar modules is equal to the Alexander polynomial of the knot evaluated at Pn. Okay, so this kind of so somehow this result convinced me that this idea is very interesting. So and now so what we want is we incorporate this into Fukaya category. So what we do is so there's a symplectic manifold on this symplectic manifold. The field is varying, and whenever you have two Lagrangians intersecting at some point, you take a Floer generator that takes values at the field at that point, right? So somehow, and so here's a picture, right? So this is the standard Floer picture. So we have a field here lambda x and a field here lambda I. They are isomorphic, but not canonically, right? And so whenever you count this thing, you count it, so you count the contribution of the monodromy of this locally constant fields, and then and you add that as a you add the kind of the contribution of that the monodromy as a coefficient.
You mean parallel transfer?
Yeah.
No.
And monodromy should go back to the same point. Is there no monodromy?
No, you have to go both ways, right? So you start from the output, you go like this, and then come back.
Is it zero then?
Huh?
Local system of local fields.
I mean, there could be like
T is the torus, right?
Only symplectic manifold.
no, in any symplectic manifold, right?
Yes.
So let me do an example. Yeah, I'm sure it's what you have in your mind. So there's only one thing that can be. So let's see an example.
What's confusing is that if you're really going to go around with this contractual, there's a disk inside.
Yeah, but it's so it's a composition of like when you.
Let me just do the example, and I'm just telling you what.
Okay. So let's do this. Okay. So here's the torus. And so what this blue line shows is that whenever you intersect that blue line, you have to apply the Fargues. Okay. So now we consider this, right? And so I have to think about the orientations, unfortunately. So probably this is. So there's this x and y. Yeah, it's right, right? So normally d of x is y minus y, right? So what's going to happen now is here we have not x only, we have d of a of x, okay? Where a is an element of the field at this point. Okay? And now here we don't intersect this thing, so we'll just get a of y. But the contribution here is minus a to the p of y.
You said we had to go back and forth.
Yes. So should I mean.
Sorry. Your differential contributes a map from lambda x to lambda y. Each disk
That's
is
right.
a map from lambda x to
That's
lambda
right.
y.
That's right.
And so you're saying you get that map by parallel transporting along either of the boundaries of the disk.
No. So let me write this formula. So let me write. Maybe that's here's. Okay, it's going to be more relevant for.
But I mean, parallel. The monodromy is trivial, right? You said you should. I mean, it's just parallel transport on one of the two sides.
Yes, one.
Right. Yes.
I think if you would do what you have in mind probably would be clearer if you had like a local system on L1 and a local system on L2, and then you take Hom between them and each intersect.
And local systems, the efficient local system
Yeah,
fields.
so then it would be more.
Right. So let me write this.
That's not what you want.
So let me just write it down.
Disconnect properties.
What? So. Okay. So how do you do this computation, right? So we look at this A. So here's what I do in practice. Okay, you take a psi here. So A is
You need another marker.
Sorry. So psi. Okay, so psi so at this point it's a home from lambda to lambda, right? So I'm going to apply a. So I'm going to apply. So there's a. Sorry, just a second. Okay, so when I pass through this, I will apply a sigma to this, okay? And then when I come here, I'm going to apply A. So I pass through here, so because of this intersection, I apply sigma, okay? Now because of this X, I apply A. Now I come back, right? So when I come back, I have to apply sigma inverse, right? So what happens? What happens is the end result is sigma inverse A times psi. And that's what A to the P is.
Can you say again what A and Xi are?
So Xi is an element here in this home space, right? Home from lambda to lambda. I want to understand the contribution of this.
Wait, Xi is home from what? From L1 to L2?
No, Xi is an endomorphism of the field in this point.
Okay, sorry.
Okay?
Yeah.
So now I want to understand the contribution of so that's kind of that's the generator, right? So I want to understand the contribution of this disk when I put A here, right? So I go around this line. So that passes through sigma, right? So I apply sigma to this psi. Then A because A is this the element that I put here, so A of x, right? So I apply A, and then I apply sigma inverse, because as I come back, I pass through this again, right? So then what happens is the psi changed by sigma inverse of A. Okay? And that's the linear map that we have. So that's the output. Is that clear now? Yeah?
Go to universal cover, actually, and copies and modal by action.
Yeah. 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 So, but anyway, so this is. I mean, I think this idea. If you're gonna remember any idea from this talk about Fargues, this is the kind of new input. So, this differential is no longer linear with a, right? So there is ay and a to by. Okay. So in particular, if you compute the cohomology of this guy, it doesn't have h1 anymore. It has only h0, right? And remember, I said the Fargues-Fontaine curve had arithmetic genus 1, so h1 was 0, and this is because this is going to be mirrored to all. Okay. So how much time do we have?
5 minutes.
Okay, so let's do. So somehow this was the second part. So let's do the third part quickly, then, because I want to. So we have a kind of an non-trivial computation that I want to show. So basically, we have now this Fukaya category, and we compute this ring. Okay. And what we get is the following. So.
Yeah, but when you get whatever to the skyscraper, then you have huge X0 and X1.
Right, that's right. So the skyscraper.
You don't have this.
So the monodromy one actually trivial, and that's always the sky.
Right. So this guy is the points, right? And it's big, right? Because as we know, the Fargues-Fontaine curve is not finite type overall, right? So
A is in F bar.
So A is going to be in our
Seriously,
A is going to be in our F. So which is so A we can choose what F is, right? And in this story, so remember I started with this E and F. This A is going to be in F. Okay. So this is this perfectoid field.
Well, how do you know that there's no H1, HF1? It's not a
Oh, because it's perfectoid, right? So perfectoid means that this thing is surjective. And so in particular it implies this surjective. So this is important that this So in fact, the story, once you have this idea and you compute it, it's kind of very similar to what we did before. The tricky part was to identify which field corresponds to which thing in the Fargues-Fontaine story. So somehow the Novikov parameter is not there. So I'd like to get there. So the Novikov parameter is a new thing, I think. So here's what happens. So we compute. Unfortunately, I'm running out of time, so let me be quick. So xm k is an element of L0 intersection Ln. Okay, and k is in Z of L. Okay. So we have now these intersections. So remember, this is L0 and this is intersections. Right? At each point there is a different coefficient, so I have to keep track of these coefficients, A and B. And I multiply them, and I compute this explicitly using this kind of triangles, not differential, but this kind of idea. And what I get is this complicated ring, right? So there is some, I'm not sure this is going to be illuminating, so let me just say there is some sigma power here of B, sigma power of on A. So don't worry about exactly recording what this is. So then T power, so T is the Novikov parameter. So remember, now our field will be F adjoint T, where F is the perfectoid field, and T is this no equal parameter. So there's T lambda, and then there's the output. xm1 plus m2 plus something. Okay? So this is a computation, explicit computation of this, this homogeneous coordinate ring, which we had done in this work 10 years ago without the sigma coefficients. Okay? So the only input is the computation of these sigma coefficients. So those are A and B changes.
T should go to some quadratic form. Yeah.
So T is a T is a quadratic form. Yeah.
Like this.
So it's like so.
A rectangle.
Right, exactly. So this is almost like a theta function, right? But it's a modified theta function by these sigmas. So what's interesting is these sigmas. And in fact, here's the way we can show. Remember, I started with the series A and Z to the n, right? So there was a ring A and Z to the n. That was this project. This thing was the Fargues-Fontaine curve. So that didn't have t's, right? So what we are going to match it? What the calculation is the following. So you take x and a times x and k. This is a Floer generator. So you send this to the following series. So you take sigma I to the a, and t m I choose 2 plus ki. This is the quadratic guy, and then z to the mi plus k. Okay, so this is kind of the. So once I give you this, you can compute those things that I didn't write. So the point is that this is a ring map. This is a ring isomorphism. Okay. So now instead of multiplying, so here we were multiplying using Floer product. Here we're just going to multiply in terms of t and z. So it's a formal series of t and z. Okay. And with this modified sigma, right? So this is a coefficients. So this is somehow coefficients in f, but there's t and z. Okay, and because formally it makes sense, and somehow because these powers are positive, and what you get is the product here is the same as the product using these series. Okay. Now to relate to this story, I have to get rid of t. Okay. So here is the interesting part. So in the usual story with the Tate curve, it's exactly the same thing where this is just A. There is no sigma I. Okay, it's exactly the same coordinates, and this is just A. And we know very well that the Tate curve, you cannot set t equals to 1, right? Because the convergence issue, so it doesn't converge. Okay, but this, the Fargues-Fontaine curve, sorry, this V that appears in Fargues-Fontaine curve, you remember this this homogeneous part. It's actually the following series are generators of it: sigma I to the a, z to the mi plus k. So this is the basis of that curve. So we want to set t equals to 1, okay? And that can be done as long as this a is the maximal ideal. Okay, so that's the kind of an interesting distinction. So if A, because what happens is maybe it doesn't converge this Z, but the sigma kind of damps so somehow, because as you apply sigma more and more, you get more and more kind of the exponential convergence. So this series actually, when A is in and the maximal ideal, it converges. And as a result, we get exactly, so if I consider Floer theory with these generators where this is in maximal ideal, I get exactly this coordinate ring of the Fargues-Fontaine curve. So that's a kind of, so is it?
It was in GCP, right?
Sorry? Yeah. Yeah. So this is equal characteristic, yes. Yeah, no, not yet, yeah. Okay.
Thank you. Any questions?
What's the difficulty in mixed characteristics?
So I don't know how p acts, but it's kind of new, so maybe it's not that good.
Particular realistic, kind of remark in New York. I said it also happened for I was getting a little bit confused. There's something called phi gamma modules, and we're thinking about this. Like you divide, it's a unit disk, and divide map z goes to z to power p. Yeah, something like this. This can be also modeled in this geometry, but it will become formal symplectic structure. It will be you divide actual by dilation, and it's like different behavior. More or less the same behavior. Decomposable with irrational numbers and so on.
Oh, yeah, I didn't get to say that. Sorry, just 1 second. So I said there's this classification of stable objects in the Fargues-Fontaine curve that was given by rational numbers, right? Obviously, those are the curves here, right? So the rational numbers gives you these curves, and those are the objects in the Fukaya category that corresponds to those.
Do you have any idea what happens if you put in a local system that's actually non-trivial in the other direction as well?
Yeah, so if you put in 2 directions, then there is another direction that it's trivial. So,
Okay.
so somehow this is the best you can do.
Okay, thank you.